Hi, everyone. All right, let's continue with our discussion of superconductivity. Here, let's go back to our outline and pick up the discussion. All right, we've introduced the microscopic theory, and we just talked about electron pairing. We saw that the electron-phonon interaction, polarization of the lattice, can lead to an attractive interaction between electrons. And we might imagine that at low temperatures, this would result in electron pairing. And we've seen that it's only a small fraction of the electrons that can participate in pairs. Those that are within h bar omega d, the Debye energy of the Fermi energy, can be paired because the interaction is so weak. Okay? Now I'd like to talk about some properties of these pairs, in particular their size. So these electron pairs are called Cooper pairs, after Leon Cooper, who constructed a theory that showed that one could get electron pairing under some circumstances. And of course, they're composite bosons. In fact, in most superconductors, the electrons pair with their spins anti-aligned, so that the total object, the Cooper pair, has a spin of 0. Of course, 0 is an integer, so that means this object is a boson, a composite boson. Okay? Now, we can use some physical thinking to estimate the size of the Cooper pairs. And here's the idea. When the electrons interact, there's a minimum interaction time. Which is set by the uncertainty principle in this way. Delta t, the interaction time, is of the order of h bar divided by the interaction energy, delta. Okay? What does that mean? It means that electrons, when they interact this way, this has to be if the interaction energy is small, this has to be a kind of long-range interaction. It has to operate over a long range. It can't be like, a collision where the two particles come together and then, bounce off of each other and exchange energy. Because the collision would take place in such a short time that the uncertainty in the particle's energy would be larger than the pairing energy delta, and so they wouldn't form pairs. It's a little bit indirect, but it gives us this physical estimate. And that means that the size should be of the order of the velocity of the electrons times delta t. How far do they move during this time? Okay? And so this is the Fermi velocity. Remember, these electrons are close to the Fermi energy, times h bar over delta. Okay? And we can estimate the size. For example, if we take a material where the Fermi energy is, say, 5 electron volts, then the Fermi velocity will be about 10 to the 6 meters per second. Very fast, right? Moreover, if the transition temperature for the material is, say, 10 Kelvin, then we'll show in a minute, this implies that delta is about 10 to the minus 22 joules. Okay? And now we have everything we need to find the pair size. And we expect this to be of the order of 10 to the minus 34 joule seconds times 10 to the 6 meters per second divided by 10 to the minus 22 joules, which gives me 10 to the minus 6 meters. So very large. So much, much larger than the separation between electrons in a material or even the pairs in a superconductor. And so this gives us a picture, like this, where these Cooper pairs are essentially overlapping with each other to form a kind of a liquid. And so the fact that this is going to be a Bose condensed liquid makes this property somewhat more complicated than an ideal gas of bosons at low temperature. Nevertheless, the most important result, the most important property of a Bose-Einstein gas does survive. This becomes a superfluid, meaning that it can move without resistance. Finally, I should mention that normally people speak of a coherence length in superconductors. The coherence length, Kc, is just 1 over pi times the thing that we were alluding to a moment ago. So it's 1 over pi times V sub f h bar over delta. And we'll have reason to bring in the coherence length again in a few minutes. Oh no, my box got completely destroyed here. Well, we get the idea. Okay, just to summarize, we found that electrons can form Cooper pairs, which are composite bosons. And these pairs, interestingly, they're rather large. We estimated the pair size, or here the coherence length, and we found that this quantity can be of the order of hundreds of nanometers. And that means that when we think of the Cooper pairs inside a metal, we have to think that the size of each pair is much larger than the separation between pairs, so that they overlap with each other in this complicated way to form a kind of a Bose condensed liquid. Okay? Here, let's look at some other results from BCS theory. The first concerns the relationship between the gap and the critical temperature. So according to BCS theory, 2 times delta, delta is the gap, should be 3.53 K Boltzmann TC. So the magnitude of the gap determines the magnitude of the transition temperature. Oh, and this would be at 0 temperature. That last thing is important because for finite temperatures, for T greater than 0, the gap decreases and the gap finally goes to 0 at T equals TC. In fact, the prediction is that the size of the gap as a function of temperature is proportional to, 1 minus T over TC. So this is interesting. Why should the size of the gap depend on the temperature? After all, the pairing interaction, this over-screening of the electrons, that doesn't depend on temperature. Well, it's because when the pairs we don't merely form pairs, we also form this collective state, this condensate. And in the condensate, it turns out in a Bose condensate that the probability to find particles in the lowest energy state is proportional to the number of particles that are already in the state. Bosons actually like being in the same state, if you will. And the more there are, the more other bosons are likely to find themselves in that state. So for this reason, the state has the property that the average energy depends on how many pairs there are in that state. And so breaking one pair doesn't just change the energy of those two electrons, it actually changes the average energy of all the rest of them. Okay? This is a phase transition to the condensed state. It's a second order phase transition, just like the transition from paramagnet to ferromagnet, where the strength of the exchange field that's aligning the spins depends on the number of spins that are already aligned. It's just like that. So the fact that the gap depends on temperature is a hallmark that the transition to the condensed state, the superconducting state, is the second order phase transition. Much like the magnetization of a ferromagnet as you drop below the Curie temperature. Okay, and just to sum up where we are now, we've shown that electrons have a pairing interaction through the electron-phonon interaction, and they can form composite bosons. We found that the size of the Cooper pairs was related to the interaction energy, and it's described by a coherence length, which we've given here. The size of the pairs can be many hundreds of nanometers, which means that they overlap to form a kind of Fermi liquid, to form this complex fluid state. We looked at some results from BCS theory. One, which we mentioned a few minutes ago, was that the size of the energy gap is proportional to the energy of the most energetic phonon. It's proportional to the Debye frequency, which is different in every material. But in some cases, we can change the Debye frequency slightly without changing the material if we make an isotopic substitution. If we substitute out a lighter isotope or a heavier isotope of the material. And in that case, we do see changes in the gap, just as predicted. We said that there was a relationship between the size of the energy gap and the transition temperature, given by this result at t equals 0. And then finally, we found that the energy gap itself is temperature dependent, and that it smoothly goes to 0 at the transition temperature when we go into the normal state. And this kind of behavior is a hallmark of a second order phase transition out of the condensed state and into the normal state. Okay, let's stop here.